Welcome back. This is our continuation class. Today we conclude our exploration of how machines learn from data. This in-depth session bridges the gap between our mathematical foundations and the application of linear regression. Given that this lesson forms the prerequisite for all future AI modules, your focused participation is vital to mastering these core concepts. For a better understanding of how this works, let's examine gradient descent in a 3D space. Imagine a coordinate system where W1 is on the x-axis and W0 is on the y-axis. The vertical z-axis represents our loss. The goal here is simple but critical. We need to find the specific coordinates of W1 and W0, where the loss is at its lowest point. The first step in the gradient descent process is the random initialization of our parameters, W1 and W0. For this example, let's assume we have initialized W1 at 3 and W0 at -2. By observing the graph, we can see the starting position of W1. As we apply the gradient descent update rule, W1 begins its iteration toward the point of minimum loss. Similarly, W0 adjusts its value, moving steadily toward the global minimum. This visual demonstration provides the intuition for how the algorithm navigates the loss surface. Next, we will derive the formal mathematical equations that make these movements. Now, let us transition to the mathematical derivation of these formulas. First, let's refresh our understanding of gradient descent in a two-dimensional space. The update rule is defined as x nu equals x old minus alpha times dy by dx. In this equation, the derivative y by dx represents the change in y with respect to x, providing us with the slope and the direction of steepest descent. By utilizing this gradient, we iteratively update x nu. After a series of iterations, the value of x converges toward the point where the function reaches its minimum value. Having analyzed the loss function, we must now establish the corresponding update rules. Since our model involves two independent variables, W1 and W0, the gradient descent algorithm requires two distinct update equations. Consider the primary update for W1. W1 nu equals W1 old minus alpha times dou L by dou W1. In this expression, dou L by dou W1 represents the partial derivative of the loss function with respect to W1. Because we are working in a multivariable space, we use the partial derivative dou L by dou W1 to measure how the loss changes with respect to W1 while holding W0 constant. This explanation on partial derivatives was provided in our previous class. The same principle is applied to derive the update equation for W0. Take a look at our final equations. Before we proceed to practical examples and more exploration of these concepts, if you have found this session valuable, please support us by sharing this video and subscribing to the channel. For additional resources, including interactive quizzes and hands-on projects, please visit our learning platform www.wisdomers.in. Building upon our previous example, let's initiate the gradient descent process. Recall that the first step involves the random initialization of our parameters. For this demonstration, we will set our initial values to W1 at 3 and W0 at -2. To better understand the impact of these choices, let's observe the resulting graph. As you can see, with these starting values, our prediction line is significantly distant from the actual data points. indicating a high initial loss. First iteration. Take a look at our equations. W1 old equals 3 and alpha equals 0.0004. Take a look at the equation after partial derivating loss with respect to W1. Take a look after substituting the values. Now, W1 new equals W1 old minus alpha times the value we got above. After calculations, W1 new equals 0.5712. Similarly, we do the same for W0 new. After the first iteration, we got W1 equals 0.5712 and W0 equals negative 2.0659. Let's observe the changes in our graph. Following the initial iteration, the updated parameters zeta W1 and W0 have shifted the line significantly closer to the data points, thereby reducing the total loss. To gain a deeper perspective, let's examine the loss surface graph to visualize how these values navigate on the surface. Let's observe the dynamic transformation of our algorithm in action. Notice how the slope W1, the intercepted W0, and the resulting prediction line evolve with each passing iteration. Upon completing 15,000 iterations, our parameters have stabilized at approximately W1 equals 0.187 and W0 equals negative 0.057. These optimized weights now form our final model, which we can use to predict tip amounts for any future bill. The fundamental takeaway here is that gradient descent serves as the bedrock of machine learning, providing the mathematical engine that allows machines to iteratively learn and improve from data. Our final prediction line is considered as y hat equals 0.187x plus 0.57. Developing a deep intuition for how weights migrate toward the global minimum on a loss surface is essential. Equally critical is observing how these parameter updates physically align the line with the data points. These twin concepts, optimization of weights and fitting line, form the foundational bedrock for understanding the entire field of artificial intelligence. We invite you to share your insights and learning experience in the comments below. Your feedback is valuable to us. We wish you a highly productive and insightful learning journey.